understanding the fine structure. So it was clear to all of you, right? I suppose. If you have any kind of question, you can ask. Probably we can discuss if there are, so that we can wait for a couple of minutes if you have some question in your mind regarding the previous class. So it was fine to all of you?
Yes, sir.
Okay, fine. So now let's start then. So are there people who are waiting, or we can start from here? Maybe I share my screen.
So you can start.
Okay. The screen is visible right now, right?
Yes, sir.
Yes, sir.
Okay. So just a quick recap. So what we did yesterday was the application of this perturbation theory. We developed this first order and second order correction formulas for the energy eigenvalues, and we applied it in the system of this realistic hydrogen atom, where we have to take into account this fine structure, and there is also this hyperfine splitting, what we will do today. So this fine structure was the combination of both relativistic correction, which include the relativistic energy of the electrons, relativistic energy equation for the electrons, and then there is the spin orbit coupling, where the orbital angular momentum couples with the spin angular momentum of the electron. So what we did yesterday in the last class is that we take the energy relativistic energy formula for the electron, we expanded it in terms of this orders of p. The first term was the usual term, and the second term was the perturbation. We treat it as a perturbation, which varied as p to the power 4. We find out the perturbed Hamiltonian. This is the h prime r part, and we calculated what is the first order energy correction due to this Hamiltonian using this formula. So after a little bit of calculation, we find out that this energy so what was the energy? Yes. So this is the first order correction due to this relativistic motion of the electron. So this happens to be dependent on n and as well as L also. So these are not good quantum numbers. So we expressed L in terms of J, where we so this was evident in terms of spin orbit coupling, where we wrote again the Hamiltonian, and we calculated the B as seen by the electron produced by the proton, and then we calculated the dipole moment. We also calculated the Hamiltonian, the perturbed Hamiltonian, and then we calculated the same energy expression, energy eigenvalue correction using the expression, and we find out that we need some of the expectation values such as 1 by r, 1 by r square, and 1 by r cube, which we did with a little trick known as the Feynman-Hellman theorem. And after all these things, we find that the total energy correction due to this fine structure depends on n and j. So, and it happens that for L equals to L plus half and L equals to L minus half, it happens to be same, which is dependent on j. So the good quantum numbers are n and j now instead of only n. And we find out that these are correct up to order alpha, which is the fine structure constant. It has a value of 1 by 137, which is quite small. And as we know that in the spirit of perturbation theory, the correction is of course uh, not dominating over the actual one. It is a little bit small correction coming from quantum effects, and this is added with the original one to get more correct value, and which is able to explain the actual real hydrogen atom energy eigenvalues in terms of experiments. Okay, so now what we will do is that we will
Sir,
calculate the high. Yes.
Sir, in the calculation of S, the mass was the mass of the electron.
In the calculation of which?
S spin.
S.
Yes, sir.
Where?
Yes, sir.
This one.
S equal to M.
Yes, mr square 2 pi. So this is the electron rotating over here, right?
So the M is the mass of the electron.
So see, so what? So this we are calculating it as seen by the electron, right? So the electron sees that there is a B, and the dipole moment of the dipole moment is of what? So the electron is within the magnetic field of the proton. So the dipole moment will be of electron, right?
Yes, sir.
So it is the electron which fills the magnetic field of the proton. So there is a magnetic field created by the proton, and the electron is within that. So the energy, that is the Hamiltonian, is mu dot B. So this mu is the dipole moment of the electron. So wherever this mu appears, it will be of the electron, right? Wherever the mass appears in the expression of mu, that will be of the electron, right? Because the electron feels the magnetic field of the proton, right?
So in the calculation of S, there
Yes.
is mr squared 2 pi by T.
Yes.
So that mass is also the mass of the electron.
Of course, everywhere there is a mass of the electron only, no?
Okay, sir.
So
So then this is just similar of the angular momentum. M omega
yes,
square R.
yes. So what happens is that so the calculation of S is done in a classical way, considering S to be behaving similarly like the angular momentum L, which has a classical analog. But you see that this mu equals to E by M times the S. This is the actual calculation. The factor of half gets cancelled in the quantum theory. So this cannot have an actual classical analog, right? Because the spin itself do not have any kind of classical analog. So if you
Okay, sir.
do the relativistic calculation, you will find that this mu comes out to be the charge by mass ratio times the spin. Because the spin do not have any kind of any kind of classical analog, this cannot be done classically. This mu equals to E by M in times S, this cannot be done classically. So but we did in a classical analog, considering S to be similarly behaving like the orbital angular momentum, but which is not true, right? Because you see the spin do not having any kind of classical analog. So so if you start from the scratch, you have to put in the relativistic theory, which is known as the Dirac theory. So this Dirac theory, you find that mu is equal to the charge by mass ratio of the particle of which you are trying to find out the dipole moment. It is only possible in relativistic theory. It is not possible in this kind of
Okay, sir.
semi-classical theory. Okay. So is
Okay.
there any confusion regarding any other kind of this algebra? Of course,
No,
what
sir.
you mentioned is correct, because spin do not have any kind of classical analog, but we treated it so that we can understand, and it is technically speaking, it is not correct to do this kind of classical S equals to angular momentum, this thing, because this is not correct. So, but we treated it in order to find whatever process we have done, but it comes out to be true in relativistic theory. So that is this Dirac thing. But you start with mu equals to E by M into S. This is only valid for spin, but if you can calculate any kind of mu for orbital angular momentum, you will find that mu equals to E times E by twice M times the L. So that is true, purely true classically, but it is not true for spin.
Okay, sir.
Okay. So any other confusion anyone facing regarding this calculation or details? Anyone? So have you tried, have any of you tried this 1 by r cube expectation value using the Feynman-Hellman theorem? Okay, so what was, so the our takeaway was that, so this is the expression for the fine structure, and it depends on J, which was not previously found out while we were calculating the hydrogen atom explicitly. And there is a crucial factor of alpha, which is known as the fine structure constant, and it is very much important in certain branches of physics. This value is very small, and this expression also depends on G. So now what we will do today is this hyperfine splitting. So this hyperfine splitting is a perturbation that is also present in the hydrogen atom itself. So today we will be doing hyperfine structure. Yeah. So this is nothing but the spin-spin interaction. Spin of proton and spin of electron interaction. Right. So of course these two particles, this electron and the proton, they both have spins, and they both interact with each other through their spin, because this spin, you can think it of course this is not true, but you can think it of as some kind of dipole which is rotating in a electric field, because you know that in a rotating dipole causes a magnet, so they have an interaction, and this thing is known as the hyperfine structure, which is even smaller perturbation compared to fine structure. So the process is similar. So what we find it out, that we find the dipole moment of the proton. First we find out what is the dipole moment of the proton. So everyone knows what is the Landis factor here. Have you heard of this term?
No, sir.
Okay, so G factor or Landis factor, this term is known to anybody, or it is absolutely new? So if not, I will explain, of course. So just a quick question, if anyone knows it, or it is absolutely new.
No, sir, don't know.
No, sir.
Okay, fine. So first of all, so if the this dipole moment of the proton is nothing but E times E by mass of the proton. Here the mass comes into picture because we find the dipole moment of the proton, mass times this, and the classical thing is that E by twice mp. So E by twice mass of the proton, and there is the spin of the proton. And what happens is that if you do a relativistic correction, you will find that there is a prefactor which is Gp for the proton. So this G is known as the Landis factor. So this Gp, okay, so let's write it as G. This is known as the Landis G factor. So what this factor is, it is nothing but the correction that you get from the Dirac theory, I mean relativistic quantum field theory. So this is the G factor, and I have put a subscript P to indicate that it is the Landis factor of the proton. So as the discussion goes, so this Ge, that is the Landis factor for the electron, is 2. That's why we wrote that after quantum correction, this expression E by twice m electron of a times s, that gets a correction factor of 2, and this 2 cancels. But this is quite not true for the proton, because the proton is not a fundamental particle, it has substructures in it, and that's why this Landis factor of the proton is an experimental input that you have to give. Of course, it has some values, but we will keep it as GP for now. So this is a constant, of course, this is a constant, but we will keep it as GP for now. So, and the dipole moment of the electron, similarly, it has mu E equals to GE by twice ME times SE. And we know that this GE is 2. So this GE equals to 2. Of course, I am very vaguely writing as G equals to 2. This had some severe corrections, which I will not go into, but to this low energy thing, this is G, this is exactly equal to 2. And this expression can be written as E by ME times SE. So this is the dipole moment of the this electron. So I hope all of you know that what is the magnetic field produced by these two by this dipole for the proton. So the magnetic field is dipole magnetic field produced by this dipole of the proton. Yeah, you have found it out, I hope, in the electrodynamics thing, that the magnetic field is nothing but mu naught by 4 pi. So somebody can say or remember, you will need this probably in your competitive exams. So any of you remember what is the magnetic field for a dipole? It is a long expression, but anybody remember?
Mu by 4 pi,
Then
2 pi a square I divided by
2 pi a squared I. Okay, so let's frame it in this way. So if you have a magnetic moment of M and it is a dipole, then what is the magnetic field due to this dipole at a radius r? You have done this thing in Biot-Savart and all these kind of things. You remember the formula?
yes.
Yes. So what is the expression?
Mu by 4 pi
Yes.
I pi 2I pi a square. A is a
Where you are getting this A?
divided by a square r square power 3 by 2.
No. What you are telling is the magnetic field for a ring at a distance r along the axis, right?
Yes.
So that is not my question. So my question is, let's say a dipole is situated at the origin. It has a dipole moment of m in terms of electrodynamics, and you want to find out what is the dipole, what is the strength of the magnetic field at a radius r from the origin.
Okay. So that will be 2 into m.
2 into m, yes. No, so there is not 2, there is 3. Okay, so they, also it can be represented as 2. So just say 2
2m divided by r cube.
Then
r cap will be the unit vector.
Then anything else? So don't you have any kind of factor as m dot r cap by r cube times r cap? Okay, so let me write it down for you, and then probably you can remember this. Mu by 4 pi r cube 3 times mu p. This is for the electron proton. It is projection on r, and there is this r minus. Okay, so just write it a little bit down. Minus mu p vector. This thing you have seen in terms of mu p replaced by m.
Yes, sir.
Yeah, so so what is this? This is the magnetic field due to a dipole situated at the origin, and you want to find out what is the magnetic field due to this dipole at a distance r from the origin, right? So everyone agrees with this formula, or it is new? I hope this is done in electrodynamics, no? The same thing happens for the dipole for the electromagnet also. This formula
Yes,
looks
sir.
similar,
Yes,
or
sir. Yes.
there is some. Yeah, so this is this dipole thing, the magnetic field due to dipole at a distance r. So what one of you said is the magnetic field due to a charged ring, right? Charged ring which acts as a dipole, of course. Uh, but the expression you said was probably the magnetic field due to this dipole, due to this ring at a radius r from the origin along the axis, right? Oh, probably one of you said this expression, right? A square plus r square whole to the power 3/2 and all those kind of.
Yes, sir.
Okay. Yes. So this thing is the due to this dipole, and there is one more term which probably you have not derived it, or maybe you have derived it. So there is mu naught, and there is mu p, and there is delta q bar. This thing you have seen. The second term you have seen.
No,
Okay,
sir.
so probably you have seen this. I just give you an analogy related to electrodynamics. So whenever you say the electric field of a point charge, so what is the electric field of a point charge at a distance r? 1 by some of you?
R square, 1 by R square.
No, tell me the full expression.
So, I mean, mu naught by 4 pi.
No, for electrodynamics. I mean for electrostatics. What is the electric field due to a charge q at a distance r?
Sorry.
Yes.
Q, Q by 4 pi epsilon naught
Yes. Then
by into R square.
I mean r square is in the denominator, right?
Yes, denominator.
Yes, and there is a r cap, right, for the direct.
Yes,
Yes. So what happens if I want to find out this electric field at r equals to 0 using this formula you have said? It is classically infinite, right? It is classically infinite, and there is a reason to it why it is infinite. But have you seen any expression such as E equals to q by 4 pi epsilon 0 1 by r square times r cap plus 4 pi delta q bar? Have you seen this expression somewhere? So
yes, sir. Yes, sir.
yes. So what is the significance of the second term? So that is written due to a reason. So what is the significance of the second term? So this is basic
যেখানে
electrodynamics. Yes.
সিঙ্গুলার পয়েন্ট অ্যারাইজ করবে where the
Exactly. So when you have some singularities in your equation, so you separate out the singularity first. So this is the so whatever you said is correct, but if you want to be more correct, you have to include the singularity also, and the singularity is written separately. So this singular point in terms of electrostatics, you have to write the expression for the electric field in such a way that it is valid for every point. So whatever you said is valid for every point except the 0, that is the singular point. So in order to include that, you also add the singular contribution, that is the delta q r minus. So if it is at r, if it is situated at r naught, so you get an expression for electric field. The first term whatever you said is right, and then 4 pi delta cube r vector minus r naught vector. You have seen this type of expression, 4 pi delta cube r vector minus r naught vector. This expression you have seen previously. or it is new to all of you? Anyone, please comment whether you have seen this expression or not in terms of basic electrostatics, not also dynamics, basic electrostatics. You have seen this 4 pi delta cube r minus r naught, this expression appearing anywhere in your problem regarding electrostatics?
Sir, may one or two problem maybe.
Yes, so you should do that problem. So that is the part, that is the singular part related to this thing. So you should also write it there. So if you want to be more correct mathematically speaking, then you should also write the singular part. The same thing happens in this magnetic field also. So you see the magnetic field is blowing up at r equals to 0. So you separate out the infinity part, and you the singular region, whatever is happening over there, that you write it explicitly, and this is nothing but the second term. So if you do this calculation in electrostatics, the same calculation if you repeat in magnetostatics, you will find the second term appears over here. But the calculation is not so trivial. You have to take a limit as r goes to 0 in a specific problem. Then only you will get the factor of 2 by 3. Otherwise, you will get infinity. So this is a nice problem you can do in your spare time. But I will proceed with this second term also. So the first term is nothing but the usual term, and the second term is the this singular part, which I have written explicitly. Okay, so then we have to find out what is the perturbed Hamiltonian. So this is, I write it as HF. This is hyperfine, and minus mu E. So this E comes because this is the electron's magnetic dipole moment, mu times B, and this is B created by the dipole moment of the proton, not due to the orbital motion of the proton. This is the dipole moment. This is the B created by the dipole moment of the proton, and it is only possible as proton is a quantum particle. It has a spin, which is not possible if proton is a classical billiard ball. That is not the case. Okay, so then what we find out, so let's simplify a little bit. So then what we have is minus mu naught by 4 pi r cube 3 mu p dot r cap mu e dot r cap minus mu p mu e minus 2 by 3 mu naught mu p mu e delta q bar. So this is the expression, and then we replace this thing. We replace this mu in terms of s, and we find out what is this expression. So this is the, okay, so there is a plus, then minus there is a minus over here because yes, mu naught by 4 pi r cube. This, there is a factor of gp e by twice MEMP. Okay, so just I factor it out. So this is gp times e squared by twice mp me, and the same expression 3 s e dot r s e dot r minus sp se minus GP squared by 2 MP ME. Oh yes, 2/3 mu naught times SP SE delta cube R. Okay, so I have just substituted mu E and mu P in terms of SE and SP respectively. And now what you have to do, you have to find out the expression for the this energy eigenvalues. So correction in energy eigenvalues due to hyperfine splitting. So we will use the same formula. So the formula I am writing over here, En 1. Okay, so just we can write it as EHF, but it is calculated in terms of nth state, so that we will keep in mind. So this is nothing but the expectation value. The expectation value is mu naught, so whatever there is there, mu naught by 4 pi GP squared 2 MP ME, and there is the expectation value 3 SP R cap AC R cap minus SPAC by R cube plus 2/3 mu naught GP square 2 MP ME SP AC. And then in order to so what this expectation value means is that we take the this one, we take the inner product with respect to whatever there is in the expression in the psi n with the state psi n, right? So this is the nothing but the expectation value. So what happens there is psi n delta cube R, there is psi n. I have written it explicitly because it will, of course there is 0, because it will pull out a term which is nothing but psi n at 0, right? Because there is a delta function over here. So just to simplify a little bit, this term, the second term, this second term will give you psi n 0 at r equals to 0, and there is the mod square, right? So this is the expression for this thing. And now I will tell you how to do this this part 1 by r cube. So 1 by r cube everyone knows. So I have written over here how to do this part in the previous day. So 1 by r cube we can calculate, but how to calculate this SPR and all this kind of things? So so this thing you can find in a similar way. So what you have to do is that you have to know a integral which looks something like this. So if you do this part, this integral thing, so you have to know this integral. Okay, so let's so we use this integral. Use this integral. So integral is 0 to pi 0 to 2 pi. You can understand that why there is pi. Pi is for the angular azimuthal, pi is for the polar angle, and 2 pi is for the um, azimuthal angle. And the integrand is, in general, let's say, if you have a dot r and b dot r and sine theta d theta d phi, because this is the solid angle, you will get an expression for 4 by 3 a dot b. Now, can any of you tell how to do this integral? If you cannot, then I will write down the steps. So, any of you can interpret how to find this integral? So can you find out how to do this integral? Any of you? A is a vector in 3D, B is also another vector in 3D, and you have to take the dot product with respect to radial coordinate. So any of you can say how to do this, or I will write down the steps. So whatever you say. Anyone? All of you can do this integral or not?
So write down the steps.
Okay, so see, so if you want to know the steps, so then speak. Otherwise, how will I know that you can do this thing or not? So this is very simple in terms of, let's say you write it as a1 I cap plus a2 j cap plus a3 k cap, and then also you write down the what is r in terms of this, and now you will find it out how to do this. Sine theta cos phi I cap plus sine theta sine phi, sorry, no, this is cos, right? Am I writing it correct, or there is cos and sine interchanged? Cos theta cap, you can find what is a dot r and b dot r, and then probably you also can integrate this thing. Okay, so if you find this 4 pi by 3 a dot b, you will find that for 1 by r cube thing, you know the expression for 1 by r cube expectation value I have written over here, and you find that for L equals to 0, it happens that this 1 by r cube is nothing but 1 by a to a cube n cube times 1 by half times 0 times 1, right? So this for L equals to 0 case, that is the without any angular momentum thing, where only the spin dominates. Okay, so let's write it down. So in the L equals to 0, where there is no angular momentum and there is pure spin, so you find out that this first term, whatever is written over here in this first term, the big expression for the this thing goes to 0. So where only the spin factor dominates. So let's write it down, and you can eventually find whatever I am saying using this formula I have written over here. So if you can find this 3 sp dot r and all these kind of things, you will see that this will cancel out. So in L equals to 0 state, it is no orbital angular momentum this means that pure spin angular momentum the first term vanishes if you do the integral whatever I have written over here. This, if you use this formula for A dot B, you will find that SP dot AC will cancel with each other because there is also some SP dot AC sitting over here. So this first term goes to 0. And we are left with the second term. So the second term is nothing but 2 by 3. So we have to write down E split hyperfine splitting equals to 2 by 3 mu naught GP square GP square 2 MP ME SP dot AC SP dot SE times psi R equals to 0 where L is 0.
Sir, there will be a minus sign, maybe.
Where?
A minus sign in the last expression of EH prime.
Overall minus sign. So I messed things up. So there is a plus, there is a plus. So where there is a minus sign?
Sir, in the HHF, there will be a minus sign. So when we get expectation,
Minus,
then
minus,
also
minus, minus. And there is a minus. Yes, yes, of course. So there is a minus sign, right? There is also will be a minus sign, no? Here?
yes, sir.
Yes. So probably there will be a minus sign. Okay, it's fine. So, so mainly we are interested in the difference in energy, but of course, if I made some mistake, you please point me out. Okay, thank you. So there is a minus sign, right? Okay. So for n equals to 0 case, so now we are calculating for the n equals to 0 because it is important due to a reason. N equals to 0 case. Oh, sorry, n equals to 1. N equals to 0. N equals to 1 eigenstate. So this is the expression for the SP dot AC up to this point. This is the expression for the hyperfine splitting for L equals to 0 case. For non-zero L, the first term will also have some contribution, but for L equals to 0 case, this is the expression. And for any general case, this expression, this colored expression is the quantity. Nothing more than that. But we are trying to find out something very important. So let's find it out. What is the energy for the energy correction for the n equals to 1 eigenstate? Okay, so for n equals to 1 eigenstate, L equals to 0, we find that this thing J is nothing but L plus S, right? So this is big J, L plus S, and L is 0, so this is only S, right? So now you have to do spin addition of proton and electron. So this is a common trick, right? So you write Sp plus Se whole squared equals to Sp squared plus Ac squared minus 2 Sp Se. Of course, these are vector squared. I have not written here. Okay.
The plus.
Plus. Sorry. So then we have sp dot ac equals to sp plus ac. So let's write it as s total spin, s squared minus sp squared minus ac squared, and there is a factor of half. Okay, so what is the expression here? E1 hf E1 hf equals to minus 2 by 3 mu naught. Okay, so 2 cancels. This is mu naught gp e squared 3 mp me half s squared sp squared ac squared, this thing. There is a average, and there is the psi r equals to 0 and L equals to 0. So if you remember the hydrogen atom wave function, the hydrogen atom for the 100 was 1 by root over pi a cube into e to the power minus r by a. So if you put r equals to 0, the exponential part goes to 1, and this 1 by root over pi a cube, if you square it, you will give pi a cube only. So this as minus mu naught gp squared 3 pi mp me a cube, and then we have half s squared, sorry, so the eigenvalues of s squared is s times s plus 1 minus sp times sp plus 1 minus se times se plus 1. So we know that this proton and electron, they are both half integer particles because they are fermions. So this expression reduces to E hyperfine 1 equals to minus mu naught gp squared 3 pi mp me a cube so there is no so all the integrations have been done for the this coordinates, so I can just put this bracket, I mean just remove this bracket, because the all the expectation values with respect to r, theta and phi has also been done. Two of them are done using this integral a dot b kind of thing, and one of them is done previously using the Feynman-Hellman theorem, that is the 1 by r cube. So there is no this expectation value remaining, and this is the absolute value. So this is s times s plus 1 minus, so half into half plus 1 is 3 by 4, and 2 3 by 4 will give you 3 by 2. So this is the expression for the this hyperfine splitting for a spin, total spin s. So let's make it a box over here.
Sir, there will be H cut square.
H cut? Where H cut? Oh, sorry. Okay, sorry. Yes, of course, there is an H cut squared. Yes, what happens is that while working with these natural units, you just forget. Okay, so there will be an H cut over here. And then you see that this expression depends on the total spin of electron and proton. And now there is an important part, that if you add two spin half particles, you probably have listened while Sir was saying that if you add two spin half particles, there are two possible states. That is the 1, 2 spin adds up to 1, and also there is the 0 state. So if it is the triplet state, then S, the composite spin, becomes 1, and this expression EHF1 gives you minus mu naught by 3 pi H cut squared. So then 1 times 2 is 2, 2 minus 3 by 2 is 4, minus 3 by 2, that is half, 1/4. And for the singlet state, S equals to 0, you have 1 equals to minus square 3 pi mp me a cube. So this is 0, so this is minus 3 by 4. And the energy difference between these two, so for triplet to singlet transition, you have delta E, there is a minus, so it becomes 1, right? This is mu naught Gp E square H cut square 3 pi mp me a cube, and there is 1. So this is the expression for the triplet to singlet transition for the ground state of the hydrogen atom. Now, why this is important? So this is important in terms of some experiments of astrophysics. So so what happens is that in case of hydrogen, first of all, the n equals to 1 state do not have any kind of splitting for the hyperfine for this thing, fine structure, right? So because there is no spin involved over here, but it has some correction from the hyperfine structure. So that is the spin interaction of the proton and the electron. So what happens is this, in terms of astrophysics, one actually observes this transition in cosmos. So you want to find what is the how much amount of hydrogen is present in terms of in a astrophysical object, and that can be find out using this transition. So what happens is that this transition, if you put all the values, so you need to put what is the value of Gp. So the value of Gp is something around 5 or something, I cannot remember. So this is the composite object, as proton is a composite object. So this Gp is something around 5. You put the value of 5. You know what is the value of E, H cut you all know, Me, MP, and A is also known. If you put all these values, it comes out to be an energy which has a wavelength lambda as 21 centimeter. So if you put all this thing, then you divide with respect to C and multiply with H to find out what is the value of lambda. You find that this becomes a 21 centimeter, and it is very useful in terms of cosmology. So it has some cosmological importance. So there are many things regarding this 21 centimeter line. So people in astrophysics try to locate this 21 centimeter frequency coming from different parts of the universe to find out various different properties. And this 21 centimeter is nothing but the wavelength of a energy transition which is happening in the ground state of the hydrogen due to this hyperfine splitting from a triplet state to a singlet state. There are many other states also. So as you know that you can have n equals to 2, 3, 4, but as you go up and up, the energy will be less and less, right? So in terms of this astrophysical importance, this 21 centimeter line is very much important. So that is the thing I wanted to mention for this hyperfine splitting. So the main expression for the correction to the hyperfine splitting is written over here. Then you have if you are dealing with L equals to 0 states, that is there is the only spin angular momentum and no orbital angular momentum, your expression for energy correction, the first terms goes away and you are left with only this second term. And in terms of hydrogen, if you again put all the values of the spins, you will get a certain expression which has some importance elsewhere, and you find that this results in a transition which has an wavelength of 21 centimeter, which is very much important in astrophysics, in one of the areas of astrophysics and cosmology. So this is the hyperfine structure, and now I will just briefly mention what are the external perturbations that you can make. So let's put it in this way. So these are now external perturbations. So I mentioned someday that there can be external perturbations and there can be internal perturbations also, which we overlooked while solving the hydrogen atom. So these external perturbations are nothing but, so hydrogen atom. Okay, so let's write it here also maybe. So hydrogen atom in external magnetic field, field B, which I write it as B external to indicate that this is an external field, and this is known as the Zeeman effect. So if you put the hydrogen atom in a external magnetic field, the levels that you already know, they further split up depending what is the strength of the magnetic field. So depending, okay, so depending on the strength of B external, you have various things, that is the weak Zeeman effect, then you have strong Zeeman effect, so what this thing is, that if your Zeeman effect is weak, I mean if your external magnetic field is weak, then the fine structure, whatever we did, that dominates, and we can treat the external magnetic field effect as a further perturbation over fine structure. If your if your magnetic field is strong enough that it dominates over the fine structure, then this strong Zeeman effect is the first order energy correction, and the fine structure whatever we did earlier, that becomes a perturbation over the strong Zeeman effect, and thus intermediate is kind of equal, that the Zeeman effect, that the external magnetic field is comparable to the internal magnetic field. So by internal magnetic field I mean the expression we calculated over here. Okay, so what is this expression? This, yes, this B. So this B here is the internal magnetic field that is experienced by the electron due to the proton. So if your B external is greater than this B, then that is known as the strong Zeeman effect. There in that case, strong Zeeman effect is dominating and fine structure is subdominating. In the weak Zeeman effect, the fine structure is dominating, that is, this internal B is much higher than the external B, and the Zeeman effect is subdominant. And in the intermediate case, this B is comparable to the external magnetic field, and then you have to do both both treatment for weak and strong Zeeman effect. So there are three kinds of Zeeman effect, so that I briefly wanted to mention. So this is the hydrogen atom in the external magnetic field, and there is also the hydrogen atom in this external electric field, that is known as the Stark effect. So these two are hydrogen atom in external electric field. Let's say this is E external. So this you can try. So I will first do this. So maybe you can try this. Okay, so you have the machinery with you, so you can try. So just let me see what is the value of this thing. Yes, so let's say you have an external electric field that is causing a perturbation H prime equals to E external times Z. So this is same as whatever problem you have done with the while doing the Dalgarno-Lewis method for the quantum harmonic oscillator. You put you give the bulb a charge and put it in an electric field. The same thing. This hydrogen atom is already charged. I mean, the electron is already charged, and you put it in a electric field. You find this is the perturbation, and if you calculate the first order energy correction to this, you will find the first order energy correction. First order energy correction due to this perturbed Hamiltonian is 0. Then you have to go to the second order, and you can find out what is the correction to the second order by Dalgarno-Lewis method. So okay, so this is the second order correction. Second order correction in energy. So I just write down the expression. So I did it way before, but probably I have this with me now. Okay, so this is En2 E1 for the, let's you calculate what is the energy eigenstate for 100 state, and you find what is the second order correction. You find that it is minus 9/4 m E squared E external squared a to the power 4 by h cut squared. So this is the thing. So this calculation is similar to the calculation probably you have tried using the Dalgarno-Lewis method. So you have to find one omega, so which commutes with the unperturbed Hamiltonian, and you have to write h prime equals to commutator of omega comma h0. So if you find, so I will just write down what is the omega, right, so that you can check whether you, so by Dalgarno-Lewis method, by Dalgarno-Lewis method, if you find the omega comes out to be cos theta times minus m E external a to h cut square time r square minus m E E external square by h cut square times r. So okay, so I can make it a little bit nicer probably. So make it a common over here, right? So if I take common, okay, so make it, so I just make it a little bit nice to look. If I take you as common, this r square plus r square by 2 plus a r. So if you find this by Dalgarno-Lewis method, you can check that your omega comes out to be this, and once you have omega, you can find out what is the expression for the second order energy correction, and that is written, I think, someday or the other. It was written. So you can do this calculation and you find out that your energy expression for the 100 state comes out to be like this. Okay, and so this is what I wanted to briefly mention. And how much time I have? 4:10. So is it fine if I carry over to or so if I take 15 to 20 minutes extra, I will end it at 4:30. Is it
Okay,
fine?
sir. Sir.
Okay, so I will just write down this expression, nothing more, so that you can do it by yourself. So this is, let's say you want to do a weak magnetic field Zeeman effect. Weak magnetic field Zeeman effect. Let's say you want to calculate this weak magnetic field Zeeman effect. Okay, so what do you have? So you see, you can proceed yourself step by step only. So what is the Hamiltonian first? The Hamiltonian due to this Zeeman effect. Z also write it only Z. So this is not um, so this is not Z component, this is the Zeeman effect Z. Okay, so this is minus mu dot B. Now B is external, so I will probably drop this external, but you know in Zeeman effect, if you are calculating, the B is the external magnetic field. Okay, so mu is nothing but the orbital angular momentum, sorry, the orbital dipole moment and the spin dipole moment, right? B dot B. Okay, and you see this orbital thing that comes minus E by twice m, and this minus E by twice m times L, plus if you consider the Dirac theory, this becomes E by m times the S times B, and this becomes E by twice m L, sorry, L plus twice S times P, right? So this is the uh, expression. Now B is B external. I have to write it. B is B external. Now in weak magnetic field, a magnetic Zeeman effect, B external is less than B created by, okay, so how to write? So B is the orbital motion so this B is that B, okay, so this B is this B, yes,
The internal.
yes, so this B is okay, yes, yes, so that can be helpful while writing. Yes, so this B is internal. So this V is nothing but the magnetic field experienced by the electron due to the proton. So this V is that V. Okay. So this is the weak magnetic field Zeeman effect assumption. So what you do is that you calculate the first order energy correction. So what you energy correction, that is EZ1. So this is nothing but the expectation value of this. So expectation value, how to find out? This is E by twice M, right? And then you have L plus 2S L plus 2S dot B external. Okay, and then you have to somehow manipulate this L plus 2S to your known eigenvalues. So that is the important thing. So that we have done twice, and now I will substitute this thing. So what I will do is that, so this becomes E by twice M. L plus S is J, so that I can write J plus S dot B external. Then we can write E by twice M. This thing, if I want to take J as common, then I have to write 1 plus the projection of S in the jth component. So this is J dot J cap by J, and then there is a J cap over here, so that becomes a J square, right, times J dot B external. Yes, I'm doing things correct. Yes, J external, and S dot J is nothing but 1 plus twice J squared J dot B external. There is a bracket. So you can write how you can write J S dot J. So you write J equals to L plus S. You bring that S to the J side, then you square it, and then you find that J squared. I am writing it, but you can do these things. J squared minus S dot J, right? So that is S squared J plus S. There is a minus if you put the other side, so this will be plus J squared minus L squared, right? And then you know the eigenvalue. Sorry, yes, the in terms of the quantum numbers, it becomes twice M. This a B external, I put it outside. B external dot 1 plus J times J plus 1 minus S times plus S times S plus 1, and for electron S is 2, so that is 3 by 4 minus L times L plus 1. This is 2 J times J plus 1, then there is a bracket and there is a J over here, right? Okay, so this is the expression. Now you can find some similarity, what I told it as a Landigi factor. The Landigi factor that you have is nothing but this quantity that you have in this bracket. So this term is a factor, it is only a factor, right? So this factor, that is 2 for the electron. If you put the values, you will find it as a 2. It will the fraction will become 1 and it will 1 plus 1 will become 2 this in this thing, and you will get a factor of 2. That's why there is a correction, relativistic correction for the electron, and the Landry factor for the electron is 2. But in terms of other things, for the proton, this Landry factor is not so simple because proton is a composite object. And then we let's say we want to find out what is the our energy correction. So if this B is in the Z direction, so let's say B is in the Z direction, then if okay, so if the magnetic field is in the, okay, so again I missed some H cut. So now you didn't tell me there will be some H cut squared, right? H cut or H cut squared, something like this. I messed things up or no? Nothing. 2, yes, there is an H cut squared, right? While putting the eigenvalues in the magnetic field is in the Z direction. Then this correction for the weak magnetic field in the Zeeman effect is nothing but E H cut squared by 2m B external 1 plus J times J plus 1 minus L into L plus 1 plus 3 by 4 by 2 into J plus 1, and this is Jz, and this Jz, you know that this is mh cut, right? Mj cut in terms of eigenvalues, Mj H cut. This is also an angular momentum, and this is the Z component of the angular momentum, and this becomes, we can write it as Ez1 equals to Gj. I am suppressing all the coefficients over here in the Gj. Then there is mu b. I will define what is mu b. And then there is B external times Mj. This is the G factor, Gj, and mu b is known as the Bohr magneton, and this has the unit Eh cut by twice m. If you put the value of this has some value, but that is not important. This is the Bohr magneton, and all the magnetic field, I mean in condensed matter physics, this magnetic field and all these kind of things are kind of measured in terms of this Bohr magneton unit, and you see that this thing depends on the mj value of the electron in a certain state. So this thing depends on the mj value of the electron in a state. So what happens is that if so let's say, let's say a specific state for n equals to let's say one state, that is 1 0 0 thing. So when n equals to 1, L, the only possible choice of L is 0, and the spin of the electron is half. So J is L plus half, and the mj values, so L plus half, that is 0 plus half, that is half. So for J equals to half, you have two possible values of mj, that is minus mj and plus mj. So what happens is that this minus mj and plus mj transition, so this so let's say for n equals to 1 state, L equals to 0, J, capital J is equals to half. That is only possible for this thing, and it has two values, mj equals to plus half and mj equals to minus half, and these two levels get splitted. So there is this transition give an electric field. So this transition can happen depending on the specific value of the magnetic field, depending on the specific value of this external magnetic field you supply as a source. So this transition only happens in terms of so if you apply external magnetic field, this is not present within the hydrogen. So you say that in terms of so if you apply external magnetic field, so this n equals to 1, L equals to 0 and J equals to half state, the splitting between mj equals to plus half and minus half, this is evident, and this electron can get transited from a half mg value to a minus mg value, and this will also emit a photon which you can detect. And you say that this happens only because of this perturbation that you supply from outside due by the magnetic field. So this transition happens only when there is an external perturbation, only when you apply external magnetic field. Otherwise these levels are degenerate. External magnetic field. So that's how you know that this is so where this is important. So this is important because this transition is happening, and this transition gives you the information of j equals to half state, and you know you have prepared your system in the ground state. So this ground state cannot have a L, so L is 0. In that case the total angular momentum is s, and you find out that there are 2 degrees of freedom for the electron, where it can stay in the half state where s equals to plus half, and it can stay in the minus half state. So that is the an experimental verification that you can find out using this splitting of the energy levels, which can only happen if you apply a specific magnetic field. So this is the external magnetic field perturbation. Of course it is weak because it is less than the internal magnetic field, and this happens if you only apply a perturbation. So this is important in experiments where you need to see what is the degeneracy of the state, and you can so if you cannot separate it out by internal perturbation, then you have to apply external perturbation in order to split it even more. So this is only happening due to this effect. So this is a very short description of this weak Zeeman effect, where this weak magnetic field is a perturbation over fine structure. I have not discussed this intermediate and strong magnetic field, which itself dominates over the fine structure, so that you can probably study if you have time by yourself. So let's wrap it up here. So if you have any questions regarding this, you can ask. So yeah, so is the hyperfine splitting clear to everybody, the calculation? This is quite easy compared to the fine structure, but it is important because it has some serious applications in cosmology and astrophysics. So that's why this 21 centimeter line, which one tries to find out, is very much important in terms of certain sectors. So is it fine to everyone, this calculation and all this thing related to whatever we have done today?
Yes, sir.
Okay. So from the next day, on Monday, probably sir will take the class. So he will introduce this many electron system. The simplest, most many electron system is the helium, and you should remember that this hydrogen atom is the only possible atom that you can solve analytically, and the analytical solution is quite large, but it is possible to have analytic solution. In any other many electron system, you cannot have analytical expression at all. So then you have to use all these approximations, but even then you cannot have analytical expression as accurate as whatever you have done in case of hydrogen atom. So that's why this hydrogen atom is important, and of course this is the main building block of the periodic table. So that's why this thing is of importance related to quantum mechanics and atomic physics. So is there anything you want to ask? You have any doubt or any kind of calculational mistake I have done probably, or anything? So all of you can access the notes, right?
Yes, sir.
Okay, so you find that there is this day 8 note previously in the folder that was shared with you.
Yes, sir.
Okay, so what I will do is that I have written it on that same note file only. So I will replace that 8, but that will contain this extra thing. Okay, this thing that is done today, that will be replaced with whatever is there till now. So I will replace that.
Okay,
So
sir.
you can see this extra class. Okay. Okay, so if there is no question, we can wrap this session up. So we will meet on Monday at 4:30. So sorry for this extra session that was decided to take this to finish this part, because from next day you will be introduced to something else, and it was quite long. So go through this calculation whenever you find time. And probably I have done it correctly. If not, there are some mistakes, factor and all those plus and minus thing. So go through this whenever you get time. It is a long calculation, and do it once so that you get how to do this kind of problems, and we can discuss it if you have any kind of difficulty related to this. Okay. So I am ending the
Okay, sir.
session now. If anybody has any question, can ask, or I can end from my side.
Yes, sir, no problem.
Okay, fine. So I am ending the session now. We will meet on Monday at 4:30 p.m. Okay, usual time.
Okay, sir.